Hey calculus fans, welcome back to another lecture. We're pretty much done with our rules of derivatives for the time being. And what we're going to do now is concentrate on what the derivative tells us about the way graphs of functions look. And that turns out to be important. We're going to talk about increasing and decreasing functions. And for the sake of intuition, we'll define increasing functions this way. The function y equals f of x is increasing if the graph of the function goes uphill as we move along the graph going from left to right. So if we move along the graph going from left to right and the graph goes uphill, it's increasing. We define decreasing functions analogously. The function y equals f of x is decreasing if the graph of the function goes downhill as we move along the graph going from left to right. And knowing in each case, notice in each case, we're moving from left to right. As we move along the graph from left to right, if the graph goes uphill, the function's increasing. If we move along the graph going from left to right and the function goes downhill, the function's decreasing. It's a pretty simplistic definition, or they're pretty simplistic definitions. But for the sake of intuition, they serve the purpose perfectly. So let's take a look at some graphs of functions and identify them as increasing and decreasing, okay? Okay, we got 4 examples to look at. The first one, increasing or decreasing. Now what I'm going to do is I'm going to move along the graph going from left to right. And as I do, as I move along the graph going from left to right, what is the graph doing? Going uphill? The graph goes uphill as we move along the graph from left to right. So f of x is increasing. Now this graph, suppose we move along the graph and we go from left to right. As we go from left to right, the graph is going downhill. That's decreasing. Again, going along the graph from left to right, the graph goes downhill. As we move along the graph going from left to right, the graph goes downhill. So f of x is again decreasing. And let's look at this last example down here. I'm going to move along the graph going from left to right. And as I move along the graph going from left to right, the graph does what? It goes uphill, right? The graph goes uphill as we move from left to right. This function is increasing. F of x, increasing. So right now we have a good intuitive feel for what the graph of an increasing function looks like and what the graph of a decreasing function looks like, and that's good. First and foremost, we want to have intuition, so we're doing good. Now, some functions increase and decrease, some of them go up and down. So we're going to look at some functions that do that and just talk about the intervals on which they increase and the intervals on which they decrease. because that's going to be important for the sake of intuition also. Okay, take a look at this function. Some places it goes up, some places it goes down. And most functions are like that. Most functions don't continue to go in one direction forever and ever. Some of them do, but most of them don't. Now, what we want to determine is the intervals on the x-axis over which f of x is increasing, and the intervals on the x-axis over which f of x is decreasing. So I'm looking at this thing, and I'm thinking, well, let's see. Apparently from negative infinity on the x-axis, all the way up to right about here, the function's increasing. So from negative infinity on the x-axis, way out here, to the point C1 on the x-axis, f of x is increasing. So I'll write that down. F of x is increasing on the intervals negative infinity to C1. And let's see. Yep, see, it's increasing, it's going uphill until it gets right about here. So until we reach C1 on the x-axis, this function's increasing. Now it seems like starting here and going to here, the function's increasing. So starting at C2 on the x-axis and going until we hit C3 on the x-axis, this function's going uphill again, it's increasing. So the interval from C1, the interval from C2 to C3, the function's increasing. And then I notice a portion of the graph right here that goes uphill. From C4 on the x-axis, the function goes uphill until x equals C5. So between C4 and C5 on the x-axis, the function's going uphill, it's increasing. And let's see, f of x is decreasing on the intervals let's see. Starting right here, the graph goes downhill until we reach this point. So between C1 on the x-axis and C2 on the x-axis, the graph goes downhill. So between C1 and C2 on the x-axis, the function is decreasing. See, any other intervals? Yeah, I see some. Starting right here, the graph goes downhill again till it reaches this point. So starting right here where x is equal to C3 and continuing till here when x is equal to C4, the graph goes downhill or it's decreasing. So over the interval C3 to C4, this function is decreasing. And any others? Yeah. Starting right here at C5, the graph goes downhill, and apparently it keeps on going down and down and down and down and down and down. So from C5 on the x-axis to infinity on the x-axis, this thing's going downhill, it's decreasing. So on the interval x equals C5 to infinity, the function is going downhill, it's decreasing. So we're getting better. See, now we can look at a graph and we can say, oh, let's see, over the interval from C3 to C4, the function's decreasing. Or from negative infinity to C1, the function's going uphill, it's increasing. And that's good. It's important to have an intuitive idea of increasing and decreasing. It's important to know or to be able to recognize where a function's increasing and where it's decreasing. Now, I'm going to keep this graph on the board, and I'm going to put some new information on here. Okay, I add to our collection of definitions. I say an x value, a value of x, and we'll say x equals c, is a critical number of the function f of x if f of x changes from increasing to decreasing or decreasing to increasing at x equals c. So if the point x equals c, if the function changes from increasing to decreasing or decreasing to increasing, we have a critical number right there, right where the function changes from increasing to decreasing or decreasing to increasing. I've taken the liberty of sort of writing the results of what we discovered a few minutes ago. On this part of the graph, I've written that it's increasing, it's going uphill. Here the graph is decreasing. Here the graph is increasing. Here it's decreasing. Here the graph is increasing. Here it's decreasing. And what we want to do now is take this definition and identify the critical numbers of this function, f of x. So in this example, the critical numbers of f of x. Well, let's see. Here the function's increasing. Here it's decreasing. So right here, when x equals c1, the graph changes from increasing to decreasing. X equals c1 is a critical number. Do we have any others? Well, here the function's decreasing, and here it's increasing. So right here at this point where x equals c2, the function changes from decreasing to increasing. So the x value of this point, x equals c2, is a critical number. And then right here at c3, f changes from increasing to decreasing. So the x value of this point, where the function changes from increasing to decreasing, is a critical number. X equals c3 is a critical number. And let's see, here the function is decreasing. But when we get to x equals c4, the function stops decreasing and it starts increasing. So right at this point where the x value is c4, the graph changes from decreasing to increasing. x equals C4 has to be a critical number. And at C5, the function changes from increasing to decreasing. So right at this point, where x equals C5, we have a critical number because right at this point, the function changes from increasing to decreasing. So those are our critical numbers. And remember how we've defined a critical number. A critical number is an x value where the function changes from increasing to decreasing or from decreasing to increasing. Now we're going to discover something else about increasing and decreasing functions. Okay, I've drawn a couple of generic increasing functions here. As we move along the graph going from left to right, the graphs go uphill. As we move from left to right, the graphs go uphill. They're increasing. And what I'd like to do is just at some random points on the graph, just draw some tangent lines and compute the slope of the tangents. So maybe right here, here's a tangent, and the slope of the tangent at that point is the derivative. Now, I think probably this point, the base of this triangle, and what I do is I take an endpoint of the tangent and the other endpoint of the tangent and make a triangle. If I go from one end of the tangent to the other end of the tangent, I go over about this much, and I'll call this 1 unit. And I'll go up, it looks like I'm going up about 1.5 units. So it looks like the change in y is 1.5 and the change in x is 1. So the slope is about 1.5. That's what I'm guessing. Not a bad guess. Good enough. Now let me draw a tangent here. Oh, by the way, remember why it is we're doing this. Our whole motivation for finding derivatives in the first place came about because we were under the impression that it's going to be very, very important to compute the slope of the tangent to the graph of a function at any point on that graph. And the slope of the tangent is given by the derivative. So let's find the slope of the tangent here. Okay. And if I call this 1 unit, then it looks like as I go from this endpoint of the tangent to this endpoint of the tangent, I go over 1 unit and I go up about 4 units. So the slope is 4. F prime of C5 is approximately 4. Now I'm going to do the same thing over here. I've drawn the tangent here. And it looks like if I go from this endpoint of the tangent to that endpoint of the tangent, I go up 1 unit and I go over 1, 2, 3, 4, 5, 6, 7. So I go up 1 and over 7. So I think the derivative is going to be rise over run. So the derivative's about 1/7. And what about, right about here, I'll draw another tangent. And I'm thinking maybe I'm going up 1 unit and over 1 unit. So maybe the slope here is about 1. Now, I guess that's enough to drive home the point. I have two functions that are increasing, and at random points I've measured the derivative. The derivative is 1 at this point. At this point, it's 1/7. At this point, the derivative's 1.5. At this point, the derivative's 4. All of these derivatives numerically have something in common. And it may not be obvious because it just may not be that shocking what it is that they have in common. The value of this derivative is rather small, 1/7. The value of this derivative, pretty big, 4. 4 is a pretty steep slope. And 1/7, not very steep at all. But if we look at the values of all of these derivatives, 1, 1/7, 1.5, 4, one thing that they all have in common numerically is that all of the derivatives are positive. And this is not a coincidence. It seems like it's a very general observation, and it is, but in this case it means something. So this is what we want to observe. The derivatives are positive. Each of these functions is increasing, and at every point on the graphs, the derivatives are positive. That's not a coincidence. Now, seeing as we've sort of discovered this cause and effect relationship, I'm going to state exactly the nature of this relationship right now. Here's the exact nature of the relationship. If the derivative is positive, then the function is increasing. That's the exact nature of the relationship. And having stated this, let me ask you something. Suppose that the derivative is negative. What do you think would be true in that case? If you're saying that the function's decreasing, you're right. So let's write that down. If the derivative is negative, then the function f of x excuse me, is decreasing. And I might throw this out. Just as a memory aid, positive increasing, negative and decreasing. It's very natural to associate these words together. Positive increasing, negative decreasing. So just note the natural association that we have. Now, can we go anywhere with this? Let's see. I think so. what happens if the function f of x changes from increasing to decreasing? Well, let's see. If the function changes from increasing to decreasing, then the derivative would have to change from positive to negative, wouldn't it? And if the function changed from decreasing to increasing, the derivative would have to change from negative to positive. So that's something to note. And maybe we should write that down. Yep, if the derivative is positive, then f of x is increasing. If the derivative is negative, then f of x is decreasing. So let's see, if f of x changes from increasing to decreasing, or vice versa, then the derivative has to change from positive to negative or negative to positive. So in other words, if f of x changes from increasing to decreasing or decreasing to increasing, the derivative has to change sign. And that works the other way around too. If the derivative changes sign, positive to negative or negative to positive, then f of x has to change direction. It has to change from increasing to decreasing or decreasing to increasing. If there's no change in the sign of the derivative, then f of x just keeps going in the same direction. On the other hand, if the derivative does change sign, the graph has to change direction, and vice versa. And let's tie something else in here too. Remember what we called the x value of a point on the graph where the function changes from increasing to decreasing or decreasing to increasing? We called it a critical number, didn't we? So let's talk about that. Remember this. The x value of a point on the graph of f of x is a critical number exactly when f of x changes from increasing to decreasing or decreasing to increasing at that point. But if f of x changes from increasing to decreasing or decreasing to increasing, the sign of the derivative has to change too, doesn't it? So I guess we're going to have to add something else to our pool of knowledge here. So we'll look at a critical number this way. We'll say that x is a critical number if the derivative changes sign at that x value. And that's equivalent to saying that f of x changes from increasing to decreasing or vice versa at that point. So if f of x changes from increasing to decreasing or decreasing to increasing at a certain x value, that x value is a critical number. But that also means that the derivative changes from positive to negative or negative to positive at that x value. So we associate a critical number with f of x changing from increasing to decreasing or vice versa. We also associate a critical number with the derivative changing sign at that x value. And we're going to look at a couple of scenarios to see just exactly what must be the case in order for the derivative to change sign. We're going to look at how it is that the derivative f prime of x can change sign at a critical number x equals c. And there are two ways that this can happen. Here's the first scenario. The derivative is continuous and the derivative changes sign at x equals c. Now, to show how this works, I'm drawing a graph not of y equals f of x. I'm drawing a graph of y equals f prime of x. So this is not a graph of f of x. This is a graph of f prime of x. And over here, we'll assume that the graph, we'll assume that f of x is positive. We'll assume that f prime of x is positive. So the graph of f prime of x is above the x-axis. And over here, we'll assume that the graph of f prime is negative. So the graph of f prime is below the x-axis over here. So to the left of x equals c, f prime of x is positive, and the graph of f prime of x is above the x-axis. And to the right of x equals c, f prime of x is negative, and the graph of f prime of x is below the x-axis. Now remember what we're assuming here. In this case, we're assuming that the derivative is continuous. And what is it that we know about continuous functions? What does the graph of a continuous function look like? It's one connected piece. It has no breaks, no interruptions. So the graph of f prime of x going from here to here is one connected piece. No breaks, no interruptions. And in the graph of f, if the graph of f of x is one connected piece, then what does the graph have to do somewhere between here and here? If the graph is really one connected piece, then we know that the graph can't go from above the x-axis to below the x-axis without doing what? It's got to cross the x-axis, right? So somewhere between here and here, the graph has to cross the x-axis, and it does that right here where the derivative changes sign from positive to negative. And that would be at the critical number. Remember, a critical number, the derivative changes sign. So where is the derivative going to change from positive to negative? Right here at that critical number. Well, this is where the derivative crosses the x-axis. So the y value of this point is 0. It's on the x-axis. So this is the point C, f prime of C, but that's equal to C, 0. So in this case, the derivative f prime of C has to equal 0. So if the derivative is 0 and it changes sign right here at x equals C, if the derivative is continuous and the derivative changes sign right here at x equals C, that means that the derivative evaluated at x equals C has to be 0. And we'll call x equals C a type A critical number. That's what we'll call it. A critical number where the derivative is equal to 0, we'll call that a type A critical number. That's my own terminology, but I use it all of the time, so remember it. If the derivative is 0, that's a type A critical number. And if x equals C is a type A critical number, then f prime of C is 0. So we saw what happened in the first scenario. Let's take a look at the second scenario. Okay, here's the other scenario. The derivative again changes sign at x equals C, but this time the derivative is not equal to 0 when x equals C. So let's see how this can happen. Over here to the left of C, the derivative f prime is positive, so the graph is above the x-axis. And over here to the right of x equals C, the derivative is negative, so the graph of the derivative lies below the x-axis. And somehow, right at x equals C, the sign of the derivative has to change from positive to negative. So right here at x equals C, the derivative has to go from positive right here to negative right there. And the graph doesn't cross the x-axis at x equals C. So how on earth is it possible that the graph goes from being positive to negative right here at x equals C without the graph of the derivative crossing the x-axis right there? How is it possible for the graph to go from here to here without crossing the x-axis at x equals C? Well, let's go back and see what it is that we're assuming here in scenario 2. F prime changes sign at x equals C. So here the graph of the derivative is above the x-axis. And here the graph of the derivative is below the x-axis. So yeah, right here the sign of the derivative does change from positive to negative. But we're told that the derivative evaluated at C is not 0. So in other words, the graph of the derivative doesn't cross the x-axis right here at x equals C. Well, how is that possible? Wait a minute. In this scenario, scenario number 2, we're not told that the derivative f prime is continuous, are we? So that has to be the explanation. The only way that the graph of the derivative can go from up here to down here without crossing the graph at x equals c is if there's a break in the graph right there. Son of a gun. The derivative has to be discontinuous at x equals c. So in this case, f prime of x is discontinuous at x equals c. And I'll go one step further. You know, there are a few ways that a function can fail to be continuous at a point. And one of the ways is if the function isn't defined at that point. And that turns out to be the case here. In this case, the derivative is discontinuous at x equals c because the derivative is not defined. So in this case, f prime of c is undefined, does not exist. So in this case, we call x equals c a type B critical number. And we've just seen the only two ways possible that the derivative can change sign. It either has to be 0 or it has to be discontinuous and fail to exist at that x value. And you know what? This is such a powerful result that I'm actually going to redefine critical number in terms of these two scenarios. Okay, here's our new definition of critical number. In light of preceding revelations, we redefine critical number. An x value, x equals c, is a critical number of the function f of x exactly when one of the following is true. A, f prime of c is 0, and in this case, x equals c is a type A critical number. Or f prime of c is undefined. In this case, x equals c is a type B critical number. This is going to be our new definition of critical number. This is going to be our definition of critical number from now on. We will not change this again ever. This is the definition of critical number that we are going to settle on. And now that we've redefined critical number, let's summarize a few points. Even though we've redefined critical number, the major properties are still true. It's still true that the function f of x can only change from increasing to decreasing or decreasing to increasing at a critical number. If we don't have a critical number, then the graph of f of x can't change from increasing to decreasing or decreasing to increasing. And secondly, the derivative f prime of x can only change sign from positive to negative or negative to positive at a critical number. If we don't have a critical number, the derivative can't change sign. Now, we will keep these two things on our list, and we will add to the list later. We need to make some more observations about increasing and decreasing functions and so forth.